Hello. As you know, this week is all about solving trigonometric equations. And if you think about all the equations we've solved so far in this course, you pretty much know how this is going to go. We are going to isolate the trig expression in the trig equation. And once we've done that, we need to apply the inverse of the given trig function. Now, I don't know if you picked up on this or not, but we haven't talked about inverse trig functions yet. Now's the time to do it so that we'll be ready to solve trigonometric equations. Now, what property does, let's say, an inverse sine function have to have? Well, it has to undo the sine function. And unfortunately, we don't have a very exciting name for the inverse sine function. We just call it the arcsine function, or sometimes we just call it the inverse sine function. Now, what property does this inverse have to have? Well, if it really undoes the sine function, then if I plug an angle into the sine function and then immediately apply the arcsine, I should get back the angle that I put in. And of course, that relationship should go no matter which order I perform that operation in. Now, we have some domain restrictions that need to be abided by for the inverse to exist. Okay? Because if we think of a sine ratio like a half, well, pi by 6 has a sine ratio of a half, but so does 5 pi by 6. So which one, if we feed in a half into our arcsine function, should it pop out pi by 6 or 5 pi by 6 or the infinitely many other accurate possibilities that have a sine ratio of a half? Well, we have to restrict it. So what we force is that whatever the output is, it has to be between negative pi by 2 and positive pi by 2. That is, the angle that finally gets outputted from an arcsine function has to have a terminal arm either in the fourth quadrant or in the first quadrant. All right, let's take a look at the graph. You do not have to memorize this graph. I will not ask you to do graph transformations on it, but you will draw it because it is really cool. So of course you know how to draw this because you know how to draw the sine curve, and then you can just reflect it about the line y equals x. That's an idea. Remember, we talked about that when we talked about inverses in general for the first time. If we think about a sine function, what does it do? Well, it takes an angle and it gives you a ratio, and that ratio is going to be between negative 1 and 1. So what does the arcsine function have to do? The opposite of that. It's going to take a ratio between negative 1 and 1 and give you back an angle, although it'll be restricted. That angle will only be between negative pi by 2 and positive pi by 2. So this graph does not go infinitely far in any direction. Those points here at, at negative 1, negative pi by 2, the graph ends right there. Or at 1 pi by 2, the graph ends right there. So my domain is from negative 1 to 1 included. My range is from negative pi by 2 to positive pi by 2 included. The y-intercept, well, we can see it's at the origin. The x-intercept, same thing, it only has one x-intercept, it's at the origin. And we have no horizontal or vertical asymptotes. I guess we can't possibly have any because of the restrictions on our domain and range. Okay. Again, you do not have to memorize this graph, it's just cool, so I thought we'd write it down. Let's take a look at the arc cosine function. Of course, there has to be an inverse function for that as well. Okay. Here our restriction, and this has a little bit to do with the cast rule if you think about it. In the fourth and first quadrants, the cosine ratios are both positive. So if I give you a cosine ratio of, let's say, 1/2, and I say the angle has to have a terminal arm or has to be between negative pi by 2 and positive pi by 2, there's actually two answers to that. You could have negative pi by 3 or positive pi by 3. So instead, the restriction we put for the output of the arc cosine function is that the angle has to be between 0 and pi. The terminal arm is in the first or second quadrant, i.e. in the first quadrant those cosine ratios are positive, in the second quadrant the cosine ratios are negative. Alright, let's draw the graph of our arc cosine function. So we're just going to go from 0 up to pi. Now pi by 2 is going to be interesting. We're going to go from -1 to 1 again, since cosine ratios can be between -1 and 1. That means our domain is going to be from -1 to 1. Now we know that the cosine of 0 is 1. So that means that we have that point. The cosine of pi by 2 is 0, and the cosine of pi is -1. So we're going to have those points there. And we get this graph here as our y equals arc cosine of x. So the domain is -1 to 1. The range is 0 to pi included. The y-intercept is going to be at 0, pi by 2. The x-intercept is at 1, 0. And we have no asymptotes again. All right, so there we have the arc cosine function. So let's talk finally about the arc tangent function. Okay. Now here our restriction is going to be that the output has to be between, or sorry, the input into our arctangent function, no, I got it wrong. The output has to be between -pi by 2 and +pi by 2. All right, so let's draw that. Now we know that x equals -pi by 2 and x equals +pi by 2 are vertical asymptotes for the tangent graph. That means they're going to be horizontal asymptotes for the arctangent graph. This is strange. We've got two horizontal asymptotes there. We know the tangent of 0 is 0. That means the arctangent of 0 is 0. And we get this strange graph right here. Again, you do not have to memorize this. I just think it's really neat. Who knows? Maybe your future teachers will mention it, and now you know what they're talking about. Now, our domain here is all real numbers, which is the range of the tangent function. Okay, no big surprise there. The range that we've got here, well, we're from -pi by 2 to +pi by 2 included. The y-intercept is at the origin. The x-intercept is also at the origin. Horizontal asymptotes, we have two. We've got y equals -pi by 2 and y equals +pi by 2. And for vertical asymptotes, well, we've got none. What a strange graph. The weirdest graph we're probably going to see in this course. Now, why are we talking about these inverse trig functions if I don't expect you to memorize the graphs? Well, we need to calculate inverse trig function values. Okay? So, if I take the sine inverse of -1/2, well, if I look to the arc sine of -1/2, it's the same as sine inverse, they mean the same thing. Okay? I know that the for the output, if I've got a negative sine ratio according to the cast rule, I'm going to get an output whose terminal arm is in the 4th quadrant. So I'm going to get a negative angle, and if I think of an angle that has a sine ratio of +1/2, I'd get pi by 6. Okay? So I want that angle, according to the cast rule, to be in the 4th quadrant, or terminal arm in the 4th quadrant. So I've got a principal angle of pi by 6, and then I apply the cast rule. Okay? Now, what does this all mean? This comes from the fact that the sine of -pi by 6 is equal to -1/2. And we're trying to swap x and y, since the inverse sine function is supposed to be an inverse. Now, for the next one, of course, special triangles will not help me at all. I'll just grab my scientific calculator and plug in the arc cosine, or the inverse cosine, of -0.4, and I'll get roughly 1.9823 if I round off to 4 decimal places. What is this telling me? It's telling me that if I take the angle 1.9823 and I plug it into my cosine function, Well, that angle has a terminal arm in the second quadrant. It'll have a negative cosine ratio, and the value will be negative 0.4. I'll put the dot over there because we did round off. Now, for the last one, if I take the inverse tangent of 10, again, I plug that in my scientific calculator since I don't recognize 10 as being a ratio from a special triangle. And I get 1.4711. What does that mean? Again, it's an inverse function for the tan function. It means that the tan of this angle, 1.4711, which is pretty close to pi by 2, just a little bit under, is roughly 10. And the closer and closer I get to pi by 2 and stay under, the larger and larger those values are going to get. All right, now we'll be using, you'll see in class, all of the stuff we talked about this week. We'll be using principal angles, the cast rule, and then these inverse trig functions, all these little pieces along with the angles drawn in standard position, SOHCAHTOA, and the special triangles to solve trig equations. We need all those little pieces put together. Thank you very much.